Hello there, I'm back. It's time for environmental science, and this is lecture number 24. We have been talking about resources, and I've been going through a lot of different resources. The next couple lectures are going to be about energy resources. So where do humans get energy from? Energy that's being used for lots of different things. Over here on the right, we have kind of a controversial look at energy on this planet. The lower dark part of the planet is all polluted and gray, and there's mining going on and burning of fossil fuels going on. And then the upper part is bright and green, and it's happy and healthy. And that is just an unrealistic, polarized view, although this is a controversial subject. There's a lot of reading to go with this, although it's kind of repetitive because all of the texts that we've been using address this issue. It's a very important issue. And to start us off, you should probably note that I'm calling this lecture, which is about non-renewable energy resources, I'm calling it Fossil Fools, because we don't seem to have a grip on the rate at which we are using this energy and the impact that it's having on the planet. And so the cartoon down here says that our most powerful renewable resource is denial. So let's take a look at what we're talking about. Okay, so energy is a resource. It's very valuable. We extract it from the earth and we distribute it and we use it for lots of different things. Shouldn't come as any surprise to you that the rate of that energy use has been increasing. Here we have a pattern over about 50 years, and it shows a pretty steady increase. This is equivalence of metric tons of oil. That's just using that as a unit. There's lots of other energetic units that could be used. No matter what unit we use, it's going to show an increase as we pass through the years. This may be a little bit more surprising. This graph kind of demonstrates that even though the amount of energy being used has been going up, the amount of energy being used per person has not. It's been pretty steady. It's always been higher, well, I should say, since the use of fossil fuels started, but it's been higher for the United States for a very long time, but it's been steady for the United States. We've got the USA, the former Soviet Union, that's the red line. Europe is green. China has been coming up in the recent past, mostly because the number of people brought it down. This is energy consumption per person, and the number of people has been kind of leveling off. And then the world is the light blue line, which shows a slight increase over this 50-year period, maybe a little bit more than that. But it's not nearly as much as we saw, just across the world. So we've been keeping pretty steady with our per capita energy consumption, but the population of the planet is still increasing. So what are we using all that energy for? Well, here's a pie diagram from a few years back showing that most of it is being used for industry. This is kind of like the water pie diagrams that I showed you that showed agriculture was the biggest use, industry was number two. Energy is being used mostly for industry. Coming in second is transportation, and then we have residential and commercial. Of course, we are most concerned about transportation and about residential. Over here, if we take the residential piece of the pie, that orange piece, and we spin that out so we can see more about it, what are we using energy for in our homes? Mostly for heating. That's space heating. And then we have water heating, and then we have appliances, which are mostly other appliances undefined. But other than those, the refrigerators seem to be a pretty big user of energy. That's for the world, okay? So industry first, transportation second, residential broken down, mostly space heating. This is for the US, and in this case, again, industry is just slightly higher than transportation. It's not quite as big a chunk as it is for the world. And then we have residential and commercial kind of tossed together into all the buildings. And of course, most of that's going to be about space heating also. So those are the patterns: industry, transportation, space heating, all around. So where is that energy coming from now that we know what we're using it for? Well, this is a time series over a very long period of time, and almost no matter where we pick in this mess, as long as we're past 1900, there are three that are the really biggest, and they're right here in the middle, taking up most of what we see today. Purple, green, and red are natural gas, oil, and coal in no particular order. Those are the fossil fuels. They are all non-renewable. And then we have a little pie diagram here to sort this out, and it says petroleum, coal, and natural gas are the three really big pieces, and then we're splitting out this green piece of the pie into renewable energy, but that's another lecture. So let's just focus on the fossil fuels here. And you can see that most of the energy that we are using today, or at least in 2013, non-renewable, can't last forever. So let's take a look at those three: oil, coal, natural gas. So this is actually a list of the non-renewable energy sources that I'm going to talk about today. And you can see coal, oil, and natural gas are on the list. I've got a couple others here. Oil, shale, and tar sands, I'll briefly mention. Those are basically modified forms of oil, but they're going to have a big influence on our future. And then nuclear, which might surprise you because that's often touted as an alternative type of energy, but it is based on the mining of uranium out of the earth, so it is in fact a non-renewable energy source. We just haven't quite decided how much of it we're going to use yet because it has some pretty big drawbacks. Anyway, those are the five that I'm going to talk about, and these are kind of the questions that I'd like to consider as we go through these. Where does it come from? How do we acquire it? What do we use it for? What are the consequences of that use, especially for the future? How much is there and how long will it last? If we can understand these things about all these non-renewable energies, we might be able to make some good decisions about how fast to use them and how hard we should be looking for renewable energy sources. All right, so the first source of energy I'm going to talk about is coal, and this says that coal is the most abundant fossil fuel in the world. What do I mean when I say fossil fuel? I mean that it is the fossilized remains of things that used to be alive. Coal is a rock, and these people are sitting around breaking big rocks into tinier pieces so that they can gather them up into baskets and carry them off, because in smaller pieces it burns more efficiently, more effectively. We can get the energy from it more quickly. So gathering these rocks and bringing them someplace where we can burn them is what coal is all about. So let's figure out how this fossil fuel, this rock fossil fuel, actually forms. Okay, and here it is. Coal comes from plants. Plants that lived on the surface of the earth in swampy areas, in shallow water. They died, they fell over, they got buried, they piled up and piled up and piled up over millions of years, and the rock on top of them and the water on top of them created a lot of pressure, and they turned into rock. This would be a sedimentary rock, and then as the pressure increased, it changed its chemical nature, which makes it a metamorphic rock. So coal is a rock. Specifically, it is a metamorphic rock. All right. And what's happening here is 100 to 400 million years ago, the plants got buried, and then all of that weight piling on top created a seam, a layer of these metamorphic rocks, which now we can dig down into. We talked about mining before. We dig down into it and create machines that dig it out, bring it to the surface, and we can burn this rock. It seems kind of strange to say that we burn a rock, but it's got so much carbon in it that it is a rock and it is burnable. Before the dinosaurs, many giant plants died in swamps. Over millions of years, the plants were buried under water and dirt. Heat and pressure turned the dead plants into coal. I think I covered it. Coal, metamorphic rock. Okay, so we dig up the coal. We take it somewhere to burn it. We get heat from it. We use that energy for various things, but it's important to remember that as a metamorphic rock, all the coal in the world has been buried for different amounts of time and has had different amounts of pressure put on it. So there's a grade of coal. There are really clean burning coals that burn really hot, and there are really dirty burning coals that produce a lot of pollution and don't give us a lot of heat. This is that grade of coal, kind of in order. Peat is what is formed from the dead plant, where it first can be called something that is rock-like. Then it becomes lignite, which has been under pressure for a little bit of time. Then it becomes bituminous coal, although there is one here called subbituminous. It's not quite considered true bituminous coal yet, but we're moving in that direction. And then finally, the last type of coal is anthracite. And you see it's a little bit shiny. That's really hard, really dense, and it burns really hot and clean. Unfortunately, that's not the most common type of coal that is out there. And so we're digging up all the coal. If you're going to dig it up, you're going to want to burn it somewhere, right? So it would be nice if we could stick to the anthracite, but we've got all these other types of coals that are also being mined and also being burned. So keep the order of these different types of coals in your mind. And let's also remember that just because we see a mine on the surface doesn't mean that coal mining is an industrial process. Historically, it's been done by people in tunnels underground. It's been a miserable practice. There are still places in third world countries where that's occurring, and it has been industrialized in many places, but people still have to be there. It is not a clean or pleasant career. It's risky, it's dangerous, and it continues to be that way. And let's not forget that getting it up out of the earth is not the last step in terms of acquiring it. Coal needs to be trucked around, and here in the United States, we tend to load it into trains, which is another process which brings it to the places where it's being used for industry and energy production. So let's make sure that we include that as part of the process of acquiring. So we are digging coal up out of the ground, loading it into vehicles, taking it all over the place to places where it can be burned. What are we using that heat for? When we burn the coal, it makes heat, and mostly we are using it to make electricity. How that works is different in different places, but most of the time it means that we are making heat that is going to boil water, and then water is going to spin turbines that generate that electricity. There's magnets and there's coils of wire involved. We talked about that energy stuff. Anyway, generating electricity. There's some other things here, but they haven't really been growing. It's the generating electricity that's been growing. Most of the electricity that you use, if you live here in the Midlands of South Carolina, most of it comes from the burning of coal. So we are using coal to generate electricity, but what are the consequences of that? It creates a lot of pollution, a lot of air pollution, because as it burns, especially if it's not that anthracite coal, especially if it's lignite or bituminous coal, creates a lot of pollution, and in some places of the world, they're not as careful about it as we have grown to be recently. I'm sure that this picture here is not a picture of a coal burning plant in the United States, because if it were polluting that much, it would be shut down. This is a picture of people riding their bicycles through a countryside where there's a coal burning plant. I'm going to have to guess in China or someplace in Southeast Asia, where there really aren't a lot of controls over what type of materials can be released into the air. And this pie diagram here shows that coal-fired power plants are a major source of hazardous air pollution emissions from 2007. And of course, it's been a while, we've gotten better, but it's not happening that way everywhere. So the biggest consequence of coal burning is air pollution. So how much coal is there? Well, if you look all around the world, we're estimating about 1 million tons, and we're dividing it here into the red parts, which are low quality coal, and the gray parts, which are high quality coal, more anthracite. And it turns out that most of it is right here in North America. So it shouldn't come as any surprise that there's a lot of people saying, hey, let's burn the fuel that we have the most access to. Unfortunately, it is in fact the biggest source of air pollution. So as we look around the world, obviously there's going to be pressure for us to figure out a way to use that fuel more effectively and more cleanly. And of course, that's why we're in the middle of this big controversy, but most of it here in North America. And the last question I said that I would end with is, how long will it last? This is a diagram from one of your texts, and it's basically showing that coal is going to be the longest lasting of the fossil fuels. And in fact, the price has been going down for quite some time, maybe because of the effectiveness or the availability of other sources of fuel, which is going to allow it maybe to last even longer. Kind of unclear. It depends on what happens with energy as a whole. But this is putting it at about 100 years of coal if we continue to use it at the rate that we're using it at. And I'm not sure what I can tell you about all this importers and exporters, and that doesn't really help me out in terms of understanding how long the coal is going to last. So I'm going to leave that right there. All right, so our next fossil fuel, our next non-renewable energy resource is oil or petroleum. It also comes up out of the ground, but it is not a rock. It comes up in a liquid form. And so we have to figure out where that liquid comes from. Okay, so this looks familiar, and it should, because petroleum is also a fossil fuel. It's also formed from pressure and heat on top of stuff that used to be alive. And it becomes fossilized, but not in a solid rock form, and it's not plants. It is plankton from the oceans, mostly phytoplankton, mostly the photosynthesizing tiny microscopic organisms. They live in the ocean, they die, they sink to the bottom, they pile up sediment. It becomes a sedimentary rock, and the pressure squeezes the carbon out of it into a liquid form. So tiny sea plants. Oh, that is unfortunate. They call phytoplankton plants. We know that's not true. So tiny sea plants and animals died and were buried on the ocean floor. Over time, they were covered by layers of sediment and rock. Over millions of years, the remains were buried deeper and deeper. The enormous heat and pressure turned them into oil and gas. Today, we drill down through layers of sedimentary rock to reach the rock formations that contain oil and gas deposits. This is an oil well, and when we hit that area where there's so much pressure on top of it, it forces the oil up out of the hole that we have drilled, and that's how we get oil. Here are some wells on the land. Here's a well out over the ocean floor. We truck it around in ships. We truck it around in trains. We truck it around through pipelines. All kinds of different ways to move it around. It is in fact a liquid, so it has to be in a container for us to transport it. But that's how we get oil into the places where we burn it. And let's find out what we're burning it for. Whoops, looks like I got a little ahead of myself here. We talked about the grades of coal that can be dug up, and there are also grades of petroleum. We have a very light petroleum and a very dark petroleum. That has to do with the density and also the sulfur content of the petroleum. And it turns out that petroleum can be separated into different layers because it's a liquid and they have different densities. So it's kind of like when oil floats on top of water. We can get lighter oils to float on top of heavier oils. We can separate it out. This is part of the oil refining process. Refining oil is basically waiting for the nastiness to settle out to the bottom and pulling the better oil off the top. And you can see here that the lighter material is stuff like butane and gasoline, and down here at the bottom we have heavy gas oil that we're using sometimes to move ships around and things like that. Anyway, lots of different types of petroleum that can be used for different purposes and different places in the world where it's drilled up. And here is the slide that says what we're using it for. Remember, with coal, it was all about electricity. With petroleum, it's all about transportation. Different types of transportation. We have diesel fuel for trucks, jet fuel for jets, gasoline for our cars. There are a few other things mixed in here, but it's transportation that is the biggest reason that we are burning petroleum all over the planet. And there are, of course, consequences. The ones that we get most outraged about seem to be when there are accidents, drilling or transporting the oil. It makes a big mess, gets in the water, gets on the land. It's gross, but of course, the biggest is there is pollution, not just from places where it's being burned industrially, but coming out as a non-point source pollution from all of our vehicles. Remember, transportation. And it may be that it's not visible in the way that these pictures show it, but it does contribute to a global problem, which is why we call it climate change, global warming. So we need to keep that in mind because petroleum contributes to that quite a bit. All right, so where is it and how are we getting it? Well, the dark areas on this map show where it's being drilled at high rates. This is where we've been getting most of it for quite some time. Venezuela here, it's got so much they don't really know what to do with it. It's causing all kinds of problems. Right now we're having this issue in Russia because this is an area where lots of oils are available. And you see that Canada is a kind of a darkish color here. That is actually, there's a lot of oil there, but it's not all in the drillable, wellable type of oil. It's more in that tar sands and oil shale, and so I'll talk about that in a minute. But it's not quite as available as some of these other types of oil. Okay, so while I'm here, let me just use this opportunity to talk about oil shale and tar sands. These are sedimentary material that contain oil, but oil shale, the oil is still kind of in between micro layers of rock, and you have to dig up the rock in order to get it out. And tar sands, where the oil is kind of all mixed in with sand, and you have to dig up the sand in order to get it out. You either have to dig those materials up, so you can't just drill a well and get it out, or you have to drill a well and pump water down into the well. The oil then washes off of this material and sits on top of the water. That requires a lot of water. That is called hydraulic fracking. And you might note that as something that's a little controversial in the news, whether or not that's safe and whether or not it's environmentally a good idea to do. Anyway, so no matter what, this is expensive oil. And you might have heard about that Keystone Pipeline issue where should it be open, should it not be open? Everybody's arguing about it. That Keystone Pipeline is carrying a lot of this oil shale and tar sands. It is expensive oil. It is not going to solve our energy crisis because it is expensive. We'll always have oil from that part of Canada because this is in super abundance, but it's always going to be expensive to extract. And you can see that here. Oil shale is in this this bar chart, one of the most expensive types of oil that we can get up out of the ground. All right, next fossil fuel, natural gas. And we don't need to worry about the state of matter of this material because it says right there in it, it is a gas. So coal, solid, rock, petroleum, liquid, natural gas, gas. But we don't need to think about where it comes from because it comes from the same place that oil does. All right, so here it is, natural gas sitting on top of an oil deposit, okay? And so if we drill a hole down into this, the gas comes up first because it's lighter, it's sitting on top of it. The gases consist of methane, ethane, propane, butane. These are burnable gases. And so they're very valuable, but you need to trap them, put them in a container right away because, you know, gases, whoop, they're gone. when we first started drilling for oil, we didn't know that. We just kind of let that stuff all head out into the atmosphere. But now we know how to trap it as we go through this process. So we're getting it from the same place. It's sitting on top of the oil. So because it's a gas, it's very important that we understand that natural gas needs to be sent in a pipeline all the way to the place that it's going to be used. So what are we using it for? Again, electric power is the highest, but it's not as high as it was with coal. It's not like taking up all of it. So electric power is the highest, but then we have industry and we have residential, and some of you might actually have gas appliances or gas heat in your house. And the reason that we can bring it into the house and burn it in appliances and things is it is a very clean fuel. So coal is the dirtiest, natural gas is the cleanest. And here we have an example of pulling it up out of the ground and then storing it in various places, maybe allowing the gases to separate the way we do with oil refining, and then it's being sent in pipes all the way to our houses and to our factories where it's being used to generate electricity or to heat, to cook, to do whatever we do with it. So it's tied to the oil industry. So as long as we're drilling for oil, we're going to be gathering natural gas, and we need to know what's going to happen to it. So here's where it is. It's not quite exactly the same as where the petroleum was, because not all oil deposits have gas sitting on top of them. You'll notice, for instance, that Venezuela, which was rich in oil, not so much in natural gas. The good news is there's a lot here in North America, and it's a clean burning fossil fuel, and we should be looking for ways to make better use of that resource. And of course, the last question, how long will it last? Well, it is in fact tied to the oil, so it's going to run out at about the same time. This is a really hard question to answer, how long will it last with natural gas, because there's lots of different ways to extract it, and some of them are more hypothetical than others. This timeline is showing that we're in the middle of kind of a level area, but then it should start going down to the point where we'll get back to where we are in 2050. So this estimate of 50 years into the future is kind of based on the same speculation. Anyway, trillions of cubic feet. That's the TCFs. That's what we measure natural gas in. Whew. Okay, last non-renewable energy source is nuclear power. This is also based on a mineral that we dig up out of the ground, but we do not burn it. It is a radioactive material, and we use it to heat up water, and we use that hot water in order to generate electricity. So nuclear power, let's take a look at how that happens. Okay, so the material we're digging up out of the ground is uranium, and it looks like a mine that we've seen before. It's usually an open pit mine, and then we're probably storing the material until the price comes up, hopefully in a safe place, because it's very dangerous. Then we're going to crush it and add lots of chemicals and thickeners to it until it becomes a solid rod that can then be used to expose that rod to water. It will heat the water up because of the radiation that it's giving off. This is a complicated process, a dangerous process, and it may be that the energy that we get from it is clean energy, but this process of extracting it from the earth and making it into these usable rods is very dangerous. And in fact, many of these places are sites that people are not allowed to enter anymore because they are radioactive. So what do I mean when I say radioactive? Well, we talked about that. This is an isotope of uranium, uranium-235. That refers to the fact that it is an unbalanced number of neutrons and protons, and so it is going to decay over time and throw off neutrons. It is the ejection of those subatomic particles that is the radiation that we talk about, and that actually causes cancer because it damages DNA. It also causes burns, but it's generally at a lower level it causes cancer. So that's what's going on. We're going to make rods out of this stuff and then hang them down into some water. You see what we're doing is pumping water down in here. The water is getting heated up and blasting out the top, spinning a turbine, which is then producing electricity, which is sent off to our homes or wherever it is that electricity is being used. Then that hot water, after it's been used to spin the turbine, comes down, mixes in with the cool water and gets cycled back. So it's over and over again, and that's why that turbine keeps moving. At some point, however, that water gets too hot and it needs to give off some steam, and that's where those big towers come in. You might see steam coming out of the top of those big towers. That's not radioactive steam. That's just hot water that's not quite hot enough to generate electricity, so they've got to have some place to let that heat go away. So that's just steam, okay? Not radioactive waste flying out of the top of those things. Anyway, this is a kind of a nice little quick diagram of how we get that electricity from uranium in a nuclear power plant. Okay, so where is all this uranium and what are we using it for? It turns out that most of it is in Kazakhstan. There's a good chunk in Canada and Australia, but beyond that, it's all in tiny amounts. What we're using it for is, as I mentioned, generating electricity, and the demand for it has been going up. However, it's been going up not nice and even the way I drew the line, but kind of with big shifts and changes in it, because every time there's some nuclear accident, people get a little nervous and investors pull their money out and then the supply goes down. But we keep coming back to it. And the question is it clean? Is this causing pollution problems? And the reality is that it's the mining of it and the creation of the rods that's creating the pollution. After the rods are created, the energy is clean, but the rods do not last forever. So we have to deal with the pollution of the mining process and the rod creating process. And the big question, what do we do with these rods after they're no longer strong enough to make electricity, but they're still incredibly dangerous? That's the problem, and that's why the demand for uranium is going up and down. So what are we doing with all this nuclear waste? Well, in the past, we knew it was dangerous. We knew we had to get rid of it, so we thought, well, let's dump it in the ocean. That's pretty deep. Turns out the oceans weren't deep enough, and we can still measure the radiation coming from those disposal sites. And in fact, here's an awful picture of some sailors because the Navy was the easiest place to get workers to help dump nuclear waste into the ocean. Many of them suffered mightily because of that experiment. Anyway, today we're not launching it into space. We're not burning it into something that's less dangerous. We're burying it. And in fact, there are many places here in the United States where tons and tons of radioactive waste are being buried under sand, behind cinder blocks, in barrels, but none of these containment methods are permanent. None of them are as long lasting as the radiation itself. So at some time in the future, there's going to need to be some new technology that's developed in order to make these places safer. And in fact, this burial of nuclear fuel includes South Carolina. We can see 4,270 metric tons of spent fuel. Looks to me like Illinois has got about the most. That's up to 9,000. Pennsylvania's got 6,000. Nevada has quite a bit, so this must be a little bit older in terms of it. But basically, these states are burying it to the extent that they can go to other states and say, if you pay us, we will bury your nuclear waste in our state. That's happening, even here in South Carolina. So that's something to keep in mind. It's not permanent. It's not forever. Somebody's going to have to deal with it at some point. Clearly, we've had some success dealing with it, keeping it out from the sites where people are living. That just can't be seen as a permanent solution. So I don't know who's going to pay the bill later on, but somebody is. Anyway, I'm done. 34. Again, I can't quite get down under that 30. I'm sorry. That's it with the non-renewable fuels. Next time it's going to be about renewables, maybe a little bit happier, but not so much solving all of our problems. Okay? I'll see you in class.